Depending on the adjustment of the potentiometer, the microcontroller can generate such a command signal. The servo lever follows the movement of the potentiometer, or both devices are rotating contrary to each other after pushing a button. That's just a software issue. You can also control a servo being modified for continuous rotation by the potentiometer. The servo motor rotates clockwise or counterclockwise depending on the adjustment of the potentiometer. The servo rotation becomes faster the closer the potentiometer gets to its maximum respectively minimum position. The servo stops whenever the potentiometer is adjusted to the center position, or at least it should stop. It's tricky to turn the lever exactly to neutral position, but when enabling a different branch of the software, the job becomes easier. There is no longer a linear correlation between the potentiometer adjustment and the pulse width signal. The sensitivity around the center position is reduced by the software, thus it is more simple to stop the servo. With the microcontroller, nearly any computer with an USB interface can be used to control servos. The home-built wiper motor servo of a previous video can be improved clearly by a microcontroller. The actual position of the servo horn is read by the microcontroller through another analog input, and the wiper motor is controlled through two digital outputs connected to an H-bridge. As demonstrated in the video about servos, those devices rotate in such a way that the magnitude of the difference between input and sensor signal is decreasing. I also talked about oscillations of the control circuit caused by a too fast movement of the servo. Here, the wiper motor is driven by an input voltage of 12V, and as you can see, the servo horn oscillates around the set point. In the previous video I reduced the supply voltage of the wiper motor to just 6V in order to eliminate those oscillations. The supply voltage of the motor can be halved by the microcontroller using a pulse width signal with a duty cycle of 50% at one input of the H-bridge. Now, there are no oscillations, but the servo speed is clearly lower than it could be. The microcontroller can be used to raise the servo speed. A simple solution is to widen the voltage interval in which the wiper motor is turned off by changing the software code. Now, the servo doesn't oscillate even at a supply voltage of 12V, but as you can see, the precision of movement is poor. That precision can be improved by using a software-implemented proportional controller. The power delivered to the wiper motor is now proportional to the difference between set point and the servo's sensor voltage. If the difference between both values is low, the motor is driven by a pulse width signal with a low duty cycle. Thus, the root mean square value of the voltage forwarded to the wiper motor is also low. The higher the difference between set point and sensor voltage, the higher the power delivered to the motor. There is a linear correlation between both values. In practice, the voltage forwarded to the servo motor can't exceed the input voltage of the control circuit, thus the curve stays at the maximum level if the difference between set point and sensor reading exceeds a certain value. In turn, if the sensor reading approaches the set point, the rotation of the servo motor is slowed down. With the software, a minimal voltage forwarded to the servo motor can be defined to avoid a too slow movement of the servo lever near the set point. As you can see, the proportional controller is a clear improvement of the Viper servo. The voltage interval in which the motor is turned off can be reduced, thus the precision of movement is increasing enormously. The servo speed is at its maximum whenever the duty cycle reaches 100%, forwarding 12V to the Viper motor. A disadvantage of this control circuit is the low power delivered to the servo motor whenever there is just a slight difference between set point and sensor reading. The torque is low near the set point, thus I can stop the servo easily. That issue can be eliminated by an integral controller. In the animation sequence, the set point is increasing abruptly. The integral controller highes the power delivered to the motor the longer there is a difference between set point and sensor reading. Once more the voltage forwarded to the motor can't exceed the input voltage. Using this kind of control circuit, the motor rotates faster the longer the set point differs from the sensor reading. A combination of proportional and integral controller highes the duty cycle and so the voltage forwarded to the servo motor whenever the mechanism gets blocked. By software, the integral component of the control circuit can be enabled whenever the servo mechanism stops before reaching the set point or if the rotational speed is lower than expected. Now, the movement of the servo is precisely and powerful. Derivative action is another improvement of the control circuit. The servo motor is fed with a higher voltage, the higher the rate of change between set point and sensor voltage becomes. Once more, the voltage at the motor can't exceed the input voltage of the circuit. The higher the slope of difference in voltage, the higher the duty cycle of the output signal. In other words, the faster the left potentiometer is rotating, the higher the voltage forwarded to the motor. Using a pure derivative control unit, the servo motor stops rotating as soon as the set point isn't changed any longer, thus as soon as the left potentiometer stops rotating. The direction of servo movement depends on the slope of error, which is the difference in voltage between set point and sensor reading. The servo lever comes to rest as soon as the potentiometer defining the set point stops rotating, thus the servo doesn't reach the set point. In order to make the servo horn follow the adjustment of the input voltage exactly, proportional or integral parameters have also to be considered by the software of the control loop. The PID controller composed of proportional, integral and derivative parameters is a clear improvement of the Viper motor servo compared to the analog circuits used in my first video about that device. If the servo is controlled by a computer through the USB interface, the set point can change abruptly in a wide range. Consequently, the motor is driven by full electric power at the beginning of the movement. Thus, a high current is running through the H-bridge and the power dissipation causes a warming of the transistors. To avoid those current peaks, a soft start can be implemented by software. Another case to be considered is a deadlock of the servo lever. Now, the integral part of the control loop highes the servo voltage to its maximum. If that is still not enough power to move the lever, the servo or the H-bridge might get damaged by the high current running through the motor. The microcontroller can detect that dangerous state and turn off the motor. Considering all those principles by the control software, the servo is moving precisely and it is largely protected from damage. If you think that's still not safe enough, you can also implement a temperature sensor using another analog input. With this wiper motor servo I have built another control loop driving the carburetor of a combustion engine. The actual revolution speed is detected via the breaker mechanism of the ignition system. The 12V of the ignition system are limited to just 3V using a voltage divider composed of a resistor and a Zener diode. The voltage peaks occurring whenever the breaker opens the circuit running through the ignition coil are suppressed by a capacitor switched in parallel to the Zener diode. Remember that a voltage above 5V will cause damage of the microcontroller. A high signal is accepted not until it lasts for more than 1 millisecond, thus the noise at the beginning of a transition is ignored. There is one pulse at the digital input of the microcontroller each revolution of the combustion engine. The number of pulses per time interval is equal to the revolution speed. You remember the sensor disk? The control loop moving the throttle lever is not a straightforward PID mechanism treated before in this video. The carburetor flap is not closed completely as soon as the given revolution speed is reached, instead it has to stay at the actual position. If the detected revolution speed falls below the set point, the throttle has to be higher, while it has to be lowered if the actual revolution speed exceeds the set point. If the measured revolution speed is within a given interval around the set point, the servo lever must stop moving. As you can see, the revolution speed fluctuates clearly, thus the control loop meets the set point only within an interval of plus minus 100 revolutions per minute. Besides the real-time processing of sensor data, the short boot time is an advantage of using a microcontroller. Cruise Control 2.0 is available right after turning the ignition key. Finally, I would like to show you a linear servo with a digital sensor instead of a potentiometer. The rotation of a geared DC motor is monitored by the microcontroller using two light sensors and a toothed disc. The DC motor is turned into a stepper motor, giving a feedback about its actual position through the sensor disc. A threaded bar is attached to the output shaft of the gearbox, by what the rotational movement is turned into linear movement. The actual position of the pulse counter is compared to the set point, and the motor is driven by the microcontroller considering those input values. There is also a proportional, integral and derivative fraction implemented by software, not to forget the emergency stop if the mechanism is jamming. The construction is simple, but not very precisely. How to improve the precision of the mechanism and some examples of use for linear drives will be treated in subsequent videos. Additional information as well as the schematics and the software is available at the project page. Thanks for watching and I'll be back.